Find the value of c that completes the square, and then rewrite each quadratic expression as a perfect square. So if I'm looking at this, in order to complete the square, we're going to take this value -2, and I'm going to take half of that, so -2 divided by 2, and that gives me 1, and then I'm going to square that. 1 squared is the number 1. So what I need to add here, c, would have to be the value 1. So z squared minus 2 times z plus 1 is a perfect square polynomial, perfect square quadratic. And if I was to write that in the perfect squared form, it would be z minus 1 quantity squared. Now it's kind of useful when you're doing this to occasionally just go ahead and generate a generic area model and verify that what you've gotten is indeed the correct factored form. So I'm going to do that by multiplying z minus 1 times z minus 1. When I fill in the parts here, I get a z squared. This is a minus 1z. This is a minus 1z. And then finally, -1 times -1 is 1. Two of these are like terms. I can combine the -1z and the -1z. And when I write that out, I do exactly get the z squared minus 2z. Those are the two that I circled in green. And then finally plus 1. So this is my answer. This is the value of c. c is 1. And the factored form is z minus 1 quantity squared. Following that pattern from the previous example, I'm going to go ahead and take 7, and we're going to cut 7 in half. So I'm just going to write that as 7/2. And I need to square that value then. So when I square that, I get 49/4. This is the value of c that will make this a perfect square trinomial. So c is 49/4. If we take a look at our notes from yesterday, they did quite a bit of stepping us through exactly what the perfect squared or the factored perfect square form would look like. For this one, it would be y and then plus, and it actually would be 7/2 squared. So in general, what we're doing here is we're taking the coefficient of our linear term, and that appears to be just landing right there inside of the parentheses, but half of it. So y plus 7/2. And again, if I wanted to check this, it's very reassuring to multiply this out. Y, and then this would be a 7/2. Y, and this would be a 7/2. When I multiply to get the area in this generic area model, this is y squared. This is 7/2 y. This is 7/2 y. And this is 49/4. The two that I can combine are 7/2 y and 7/2 y. When I add those up, I get 14/2 y, which is exactly 7y. So the answer written out is indeed y squared plus 7/2 y, and 7/2 y is 7y. And then finally, that upper right-hand corner is plus 49/4. Question 10, the directions say solve each equation by completing the square, and please give your answers in exact form. So to complete the square, the first thing that I end up doing is I add 59 to both sides to create a space where I can complete the square. So when I do that, on the left-hand side, I have n squared plus 20n plus some yet to be determined value, and that will equal 10 plus 59, or 69. And what I do next is I'm going to take half of 20, which is 10, and square that. So to complete the square, I'm going to add 100 to each side. On the left-hand side, that is now a perfect square trinomial, and it actually is n plus 10 quantity squared. the left-hand side is 169, which is a perfect square. If I take the square root of both sides of that, on the left-hand side I get simply 13. And on the right-hand side, when I take the square root of a perfect square, I switch to the absolute value function. And again, my justification for that is anytime I take a value, it could be x, for example, and I square that, and then I take the square root, what it does is it removes the fact that the number was positive or negative, right? This function, squaring or taking the square root of a perfect square, is equivalent to the absolute value function. They always have the same values. What I like about this now is I can look at, I've got the absolute value of x plus 10, and if I look inside, I know that this value inside can be either positive 13 or negative 13. If it's positive 13, the absolute value of that would be 13. And if it's negative 13, the absolute value of negative 13 is also 13. So that allows us to rewrite this into two separate equations. One of them is x plus 10 maybe 13, or the thing inside x plus 10 could be negative 13. If we add 10 to each side, one of our solutions is that n could be the number, we're subtracting 10 from each side, n could be the number negative, no, it would be positive 3. 13 minus 10 is positive 3. And over here, if I subtract 10 from both sides, I get that n could also be negative 23. So either of these values would solve the original quadratic. And it's always worth it to plug that in, square it, and then add 20 times it and subtract 59 and verify you get 10 for both 3 and negative 23. Again, I'm going to begin by subtracting 4 from each side to create a space. When I do that, this becomes m squared minus 6 times m plus some value, and that will equal 8 minus 4 over on the other side. The value that I need to complete this square is half of negative 6, which is negative 3, and negative 3 squared is 9. So I'm going to add a positive 9 to each side here. On the left-hand side, that is a perfect square now, and if I write that as in its perfect squared form, it would be m, and then minus half of 6m, or minus half of 6 would be minus 3 squared. And over on the right-hand side, I have 8 minus 4, which is 4, plus 9, which is 13. Unlike the previous problem, this is not a perfect square. So when I take the square root of both sides, on the square root on the right-hand side is the square root of 13. And over on the left-hand side, the square root of m minus 3 quantity squared, again we go to the absolute value function. Looking inside, m minus 3 can either be positive root 13 or it could be negative root 13. So I'll write m minus 3 equals root 13, or m minus 3 equals negative root 13. And if I add 3 to both sides, we see that m could either be 3 plus the square root of 13, or m could be 3 minus the square root of 13. And finally, the last group asks us to find each product. This is I guess the worst. It's not the worst case scenario, but it's certainly the most complex of the three. Anytime I go beyond pretty much a monomial times a binomial, I like to use a generic area model just to kind of organize my work. So I have a trinomial times a trinomial. So I'll have 3 columns, and I'll also have 3 rows. And I'll take the first 3 terms as my column header, so I'm going to write a 4 times k squared, and then a positive 3k, and then finally a 5. And for the other trinomial, we had a k squared, and then minus 3k, and then minus 2. So as we multiply through here, in the first upper left-hand corner, I've got a k squared times 4k squared, which would be 4 times k to the fourth. Directly below that I have 3k times 4k squared, which would be negative 12k to the third. And below that I would have, when I multiply 4k squared by negative 2, I get negative 8k squared. And the middle column, top one, is going to be 3k to the third. Below that I would have minus 9k squared. Every single one of these is simple, right, by itself. It's just a matter of being careful and getting the correct products. When I multiply negative 2 times 3k, it's minus 6k. And then our last column, top row, we have a 5k squared. Below that we have minus 15k. And below that I have the number negative 10. Now, several of these are like terms. In fact, the way it turned out, there's kind of a pattern on these diagonals. Minus 6k and minus 15k are like terms. They can be combined. Also, 5k to the second and negative 9k to the second and negative 8k to the second are all like terms. They also can be combined. Also, we've got a 3k to the third and a minus 12k to the third. They can be combined. So when we combine our like terms and write our answer, the product is, starting in the upper left-hand corner, 4k to the fourth power. And then when I combine negative 12k cubed and positive 3k cubed, I get a negative 9k to the third power. And then in blue I've got, let's see, negative 8k squared and negative 9k squared is negative 17k squared. If I add 5 to that, I believe I'm sitting at negative 12k squared. For the green ones, I end up getting negative 21k squared. And then finally I have a minus 10. So you can see our like terms here. We have the k squareds. There should be 21 of those. I'm sorry, those are just the k's. I said k squareds. Those are just the k's. We have our k squareds, and those, there should be negative 12. And then finally we have our k to the thirds, and that should be a negative 9. The other two, the 4k to the fourth and the negative 10, weren't like terms with anything else, so we just write them by themselves.